Hi, welcome to a problem that we're going to do here. My office high atop building D on Scott North Wake campus at Wake Tech. So this problem here, we're said given a linear transformation from R3 to R3 defined by this function here, t of x1, x2, x3 is equaling x1 plus 3x2 comma 3x1 plus x2, comma 2, negative 2, negative 2x3, right? And so we've got that linear transformation. And so our task is to determine the eigenvalues and eigenvectors associated with the standard matrix of T. And then once we do that, we want to determine the matrix of T relative to the complete set of linearly independent eigenvectors. Right? There's an example. Actually, this is very similar to an example that is the very last example from chapter 7, section 1. And there are a couple of homework problems from 7.1 that are similar to this. So the first thing we need to do is we need to get that standard matrix. Okay. And so the definition, by the definition way of doing that is to determine, well, where are the basis vectors being taken by the transformation? So again, our basis vectors are going to be 1, 0, 0, 0, 1, 0, and 0, 0, 1, the standard basis. Okay, so and those vectors, those images, are going to be the columns for matrix A. So 1, 0, 0. So again, we're letting x1 be 1, and the other two variables are 0. So plop that in. This is 1. That's going to be 3. And of course, that's going to be 0. So we get the first column is 1, 3, 0. Then we will look and see, well, where does 0, 1, 0 go? 0, 1, 0. That'll be 3. That'll be 1, and that'll be 0. And then 0, 0, 1, well, these two are going to be 0, and then we'll have negative 2. So there's our matrix. So now we've got to find the eigenvalues and eigenvectors. So first thing to do, get the characteristic equation. So the characteristic equation, the way I write that is I take the determinant of A minus lambda I and set that equal to 0. Now our textbook, and you may see some other sources doing this as the determinant of lambda I minus A. Either way, it comes out the same. It's just that this direction, all you have to do is subtract away lambda from the main diagonal elements. And you don't have to do anything else. If we do it as lambda I minus A, then we also have to change the sign of all the other off diagonal elements, which can be a bit much. And if you know your limitations, like I know my limitations, I know that I'm probably going to forget one. There's going to be some sort of error that I'm going to make. So this way, not quite so many places for that. All right, so we're going to take the determinant of, this will be 1 minus lambda, 3, 0, 3, 1 minus lambda, 0, and 0, 0, negative 2 minus lambda. Okay, take the determinant of that, set it equal to 0. So this is nice because we can expand by minors and cofactors along the third row or the third column. Because again, a lot of zeros here. So this is going to be negative 2 minus lambda times the determinant of 1 minus lambda, 3, 3, 1 minus lambda. So I can factor, well, I'll leave that as is, negative 2 minus lambda. And then here, this is going to be 1 minus lambda squared minus 9. Well, that's a difference of perfect squares, so that factors nicely. This will be 1 minus lambda minus 3 and 1 minus lambda plus 3. doing a little bit of work here, we see that here I get -2 minus lambda again. Okay, so I get -2 minus lambda squared. Well, squaring the opposite is the same thing. I get the same thing as the square, the opposite of the opposite. So I could write this as 2 plus lambda squared, and this is going to be 4 minus lambda. So we get two eigenvalues, -2 that's repeated and 4. Okay, so I'm going to erase this real quick. Give us some room here. So now we've got our eigenvalues. Now we want to get the eigenvectors. Okay, the eigenvectors are basically solving this this equation here, that a v equals lambda v. Of course, I can subtract v from both sides and factor it out. I mean, subtract lambda v from both sides and factor it out. And so we get that system that we're trying to solve. So let's plop in -2 for lambda. Okay. So that gives us 1 minus a -2. So that's 3, 3, 0, 3, 3, 0, and 0, 0, -2 minus a -2. That's 0. Okay. Then we can get that in row echelon form. Comes out rather nicely. Okay, and again, if you didn't see how that was going to happen, you can always plug that into a calculator and get it to reduce it for you. Okay, but anyway, that comes out really nicely. We only have one column that has a leading 1. The other two don't. So that means that we're going to let x2 equal a parameter s and x3 be a parameter t. We need two parameters here. And of course, this top row is telling us that x1 plus x2 equals 0. So we know that x1 and x2 have to be opposites. So we know that x1 has to be -s. Right? So if we look at our s's and t's here, we're going to have -1, 1, 0 times s plus 0, 0, 1 times t. All right, because if I look at what x1 is, it's -1s plus 0t. Aha. And then x2 is 1s plus 0t. Aha. And x3 is 0s plus 1t. There we go. So we have, what we have here are two linearly independent eigenvectors associated with this one eigenvalue, that lambda equals -2. Okay, that's nice. That's nice there. If we look at lambda equals 4, okay, we plug 4 in for lambda. We've got -3, 3, 0, 3, -3, 0, and 0, 0, -6. All right, we reduce that. We see we're going to get 1, -1, 0, and 0, 0, 1, 0, 0, 0. All right. So now we only have one column that has a that is absent a leading 1, a column that doesn't have a leading 1. So x2, we'll let that be t. And then we see that here that says x1 minus x2 has to equal 0. So x1 has to also equal t. And then x3 has got to equal 0. So the parameter of the vector that we get, the eigenvector that we get, is 1, 1, 0, of course, times t. So again, the basis that we have, I'm sorry, take a step back here. So the eigenvectors that we have -1, 1, 0, 0, 0, 1 associated with lambda equals -2. And then for the lambda equals 4, we get the vector 1, 1, 0. Okay, one little extra thing to note here is that this lambda equals -2 produced two eigenvectors that were linearly independent. Well, the only reason why that could possibly happen is because our factor was repeated, was raised to the second power. So we had a eigenvalue, we say it has an algebraic multiplicity of 2. And so that can produce two vectors, two eigenvectors, or it could produce one eigenvector. Okay, when it produces two eigenvectors, we say it has a geometric multiplicity of 2. And so this one had an algebraic multiplicity of 2, but it also had a geometric multiplicity of 2. Lambda equals 4, well, it had an algebraic multiplicity of 1, but also a geometric multiplicity of 1. Whenever you have an eigenvalue with algebraic multiplicity of 1, the geometric multiplicity has to be 1. But bigger than that, it can be any integer below or any positive integer. Okay. All right. So we've got our set of eigenvectors here. They are a linearly independent set, so they do form a basis for R3. And if you recall, the second part of the problem was to write the matrix associated with the linear transformation referencing these eigenvectors as a basis. Okay, so again, as we did with the start of the first problem, is we'll say, well, where do the vectors go? Where do the vectors get taken? So we will look at where does -1, 1, 0 go? Okay, where does -1, 1, 0 get taken? Right. So that gets taken to where does it get taken? Easier said than done. So this goes to -1 plus 3 times 1. So that's going to be 2. Then -3 plus 1. So that's a -2. And then over here, I got just 0. Okay. And then look at the next one, 0, 0, 1. So there, this gets taken. Again, the only thing that's not 0 is x3. So that's going to be 0, 0, and then -2. And then we'll look at 1, 1, 0, 1, 1, 0. So here I get 4, 4, 0. So we're just about done. We've got the images of the basis vectors, but there's that one extra step that we've got to remember, is that we've got to write these vectors with respect to this basis. In other words, we have to figure out what are the coordinates of each of these vectors with respect to these vectors. In other words, we have to write each of these vectors as a linear combination of the vectors inside here. But this is a lot easier than it sounds, because let's look at it. -1, 1, 0. Well, if I multiply that times -2, hey, look at that. Okay. So really, all I need is -2 of these guys, but none of these two. So the vector that I would have would be -2, 0, 0. Let's look at the next one. 0, 0, -2. Well, I've got to write it as a linear combination of these three vectors. Oh, but look at this. This vector right here is 0, 0, 1. Hey, that's -2 times 0, 0, 1. Now that's the middle vector of the three. So that's going to be 0, -2, 0. Again, the reason why this one was first was because we listed the -1, 1, 0 first. The reason why this is second is because the 0, 0, 1 was second. Okay. And then, hey, this looks pretty nice. What about this one? 110, 440. Hey, I could take 4 times 110 and get that. So here we get the matrix, the coordinate matrix here. Sorry, there should be equals there. But the coordinate matrix there is 0, 0, 4. Because it just takes 4 of these this last one to make it. And so the matrix that we would get is formed by those columns, those vectors as columns. Oh, isn't that nice? It's a nice diagonal matrix. And, oh, look at that. The numbers on the diagonal are precisely the eigenvalues. Oh, and even better still, the one that got repeated, it shows up twice. How about that? It's not a coincidence. Okay, it's not a coincidence. This is going to happen. Whenever you wind up with having the same number of eigenvectors as you have, basically rows and columns of your matrix A, this is going to happen. And if we think back to the idea of similarity, that tail end idea from chapter 6, it's even better. Because we have this A here. Okay. So the A prime here is equal to P inverse A P, where P is going to be the matrix formed by the eigenvectors. A is the original matrix that we had at the beginning of this problem. So we have that this particular matrix A is going to be similar to a diagonal matrix, which comes in really handy and is the basis for section 2 of chapter 7. Okay, so I hope this helped and good luck. If you have more questions, give me a holler.